All right, we're gonna look at the log function's homework. So when we read this statement here, we're saying x is equal to log base b of a. And what this describes is an exponent. So if we have something like log base 2 of 8, this is equal to the exponent that when you take 2 to it, you get 8. So this is really the number 3, just another way of writing that. If I have something like log base 5 of 25, again, that's saying 5 to what power makes 25, which answer is just 2. So log base 5 of 25 is really just another way to represent the number 2. And log base 2 of 8 is another way to say number 3. Okay, so for number 2, we're going to convert the equations between the exponential form and the logarithmic form. So state in words what each logarithm describes. So we have this log base 4 of 16 equals 2 is really 4 to what power gets you 16, and that would be the exponent of 2. So when we're looking at 3 to the 4th equals 81, that's log base 3 of 81, and that's equal to 4. Again, this number 3, that's our base. 4 is the answer to a log, and then 81 is the answer to an exponent, that whole flip-flop thing. Okay, so really, again, it's saying like 3 to what power is 81, and the exponent or the power is going to be the 4. So our log base 3 of 81 is 4. All right, log base 27 of 3 is equal to 1/3. So again, we're saying 27 to what power gives 3? And that power or that exponent is 1/3. So we're saying 27 to that 1/3 power will equal 3. And again, reminder that 1/3 is the cubed root. All right, the next one, 5 to the negative 2 equals 125. So we're saying 5 to what power gives that 1/25? That's the question. And the answer to that exponent is negative 2. So we just write log base 5 of 1/25 will equal negative 2. And then again, a reminder that negative exponents flip it and give you that reciprocal. Okay, so log base 8 of 1 equals 0. That is saying 8 to what power gives 1? And that exponent would be 0. Again, I'm reading and trying to figure out what that log form means. So 8 to that 0 power will equal 1. So 8 to the 0 equals 1. Okay, so we have bx equals a. That's, again, saying b to what power gives a. I mean, we can see it in that exponential form. But really, that's what the log is asking you. Log base b of a is equal to x. And so that exponent is x. B is the base, x is the exponent, and a we call the argument. Okay, so the next few we're trying to evaluate these. So it wants us to try and set each logarithm equal to x, because that helps us think about things. We're saying like 3 over 2 to what power, and we use x here, will get us 4 over 9. Well, notice that they are kind of related. 2 to the second power is 4, and 3 to the second power is 9, but it's kind of flip-flopped. So remember the thing that flip-flops is a negative power, and because we said it was 3 times 3 makes 9, and 2 times 2 makes 4, that's to the second power. So negative 2 will be the answer to this, because if we take 3 over 2 to the negative 2 power, and we'll flip it because it's like 1 over that, and then it will square it. 2/3 times 2/3 is 4/9. All right, for the next one, again, if we say equals to x or question mark, however you want to do that, it's saying 5 to some power will be 1 square root of 1/5. So just a little reminder here that that square root is a 1/2 exponent. So really it's 1/5 to the 1/2 power. And so when I'm like trying to think about what x could be, it has to be something related to 1/2. Notice that it's putting 1 over 5. That's a reciprocal. So I think negative 1/2 is what's going to make the most sense here. So let's see. I boxed it already, but let's check. 5 to the negative 1/2. So remember that negative exponent puts us as reciprocal. And then we have to the 1/2, which that's what its meaning is, the square root. All right, for number 4, it wants us to find the domain of the following logarithms, and it does have a little reminder here that the argument of a log must always be positive. It can't be negative and it can't be 0, so that inside portion here. So we don't really need to know much about the base. We just want to make sure that x squared minus 16 is staying positive, so it's staying greater than 0. And so there's a couple different ways that we could think about that. I'm kind of drawn to, we've been working with the polynomials and trying to figure out whether positive and negative. And so if you look at this, we want to know where we're greater than 0. So if I can find the zeros of x squared minus 16, that would be great. So when does x squared minus 16 equal 0? And again, you can solve that a few different ways. If I factor, that's the difference of squares, x plus 4, x minus 4. So that's going to be at negative 4 and 4. So if we're thinking about this picture, we know we touch at negative 4 and 4, and our graph is upward facing parabola because there's no negativity there. And so you can see we're going to be plus, minus, plus. So the space that we want is for us to always be greater than 0. So that's going to be the portion where we're less than negative 4 or we're greater than positive 4. So if I write those two intervals, that's from negative infinity to negative 4, not including negative 4 because that would equal 0, and then from 4 to infinity. So if you pick any numbers in those intervals, you're going to end up with a positive result. Again, that's working because we square it, so all that negativity will become positive. All right, for this next one, we're looking at the square root of x plus 5 minus 1. We want that to be greater than 0. Again, there's a few different ways you can think about that. Really quick in my head, I'm trying to imagine what this graph looks like. We haven't solved inequalities with that square root, but if I think about the picture, this is a square root function, so we know it like starts at 0, 0 normally and then like shoots off, but it's transformed. It's moving left 5 and down 1. And so left 5, 1, 2, 3, 4, 5, down 1. And if I get another point on there. So we're kind of talking about that picture there. And so we know that we are negative up until whatever that point is, and then we are positive. Looks like that's at negative 4. Just to check, I can solve the equation and find the 0. Square root of x plus 5 plus 1 to both sides, plus 1, plus 1. That's going to be equal to 1. If you square both sides, that's x plus 5 equals 1. Minus 5, we get x equals negative 4. So that point where they change signs is going to be at negative 4, because again, that's the 0. We just found that. And so we're going to say from 4 to infinity, and we don't want to include the 4 because that's where we equal 0. So that graphing that we worked on so much is really helpful for problems like these, so we can think about graphically what's going on without having to solve these inequalities with the algebra, really. Okay, for the last ones, we're going to graph. For all of them, when we graph the logarithms, it's nice to think about the parent function and its inverse. So the parent function here really is going to be that log base 3. So y equals log base 3 of x. And that negative is doing that reflection over the x-axis. The minus 1 is moving us to the right 1. And then we're moving down 3. So we have a lot of stuff going on there. So So when I think about the parent function log base 3 of x, I actually want to graph, or at least make a table for its inverse. Remember, log is the inverse of the exponential function. And so if I make a small table, like we did in the other homework, put a 1 in, we get 3, a 0, and we get 1, we know without working too hard the table for the parent function, log base 3 of x. We just interchange those values because they are inverses. So I know the parent function would have 3, 1, and 1, 0, and it has a vertical asymptote now. I'm drawing this dotted just because that's the parent function. So that's what log looks like. And again, it has that vertical asymptote. So if I want to interchange, or I already did it, the interchanging, what I mean is the next step is reflecting over the x-axis. So now, I mean, I have that main point, 1, 0 still there, but instead of 3, 1, it's negative 3, 1. And so you can kind of imagine it just reflecting over. So that's the negative log base 3 of x. But then we have to do those other transformations where we move right 1 and then down 3. So if we move right 1, that's going to make our vertical asymptote now at x equals 1. So I'm going to put that in. We'll note of that, x equals 1. And then all my points have to move, again, we're looking at the green graph, to the right 1 and down 3. So move this little dot, right 1 and then down 1, 2, 3, puts us here. Right 1 and down 1, 2, 3, puts us here. And so the picture that we're getting, like a backwards looking J, that's the picture of our graph. This is going to be our f of x. So our parent function, we already put that, was log base 3 of x. The domain is not negative infinity to infinity anymore. It stops with that vertical asymptote, so it'll be 1 to infinity. And the range, though, is negative infinity to infinity. So these are all kind of the opposites of our exponential function. All right, last one here. We have 3 log 2 of negative x. So the negative inside does a reflection, but this one is over the y-axis. And then we also have the 3 in the front. That's a vertical stretch. And so our parent function is going to be that y equals log base 2 of x. And again, I like to think of its inverse just because that's super easy. And maybe you skip this step, but it's really nice to just plug in a 1 and a 0 and see what happens. So 1 gets me a 2, a 0 gets me a 1. So then I know for my parent function, the table would be 2, 1, 1, 0. Okay. It's a little roundabout way, but it always works. And it's nice to be really comfortable with that 2 to the x to help us graph these logs. So 2 to the 1, or 2, 1, and then 1, 0. So that is the parent function. And so we're reflecting over the y-axis. So that means that instead of being at 2, 1, we're going to be at negative 2, up 1, and then 1, negative 1, 0. So just the reflect part is this guy. But then it also has to vertically stretch. So instead of going to the up 1, left 1, it's going to be going up 3 spaces because it's triple that value now. So it's going to be at the 3 because, again, it's triple. And the point negative 1, 0, there's no y value. I mean, the y value triple is 0, so that's going to stay in the same spot. So I have this point here at 3 and that point here at negative 1. And so my final going to be that guy with the vertical asymptote. We didn't move left or right. We just did that flipping and stretching. And so it's going to be still at x is equal to 0. Parent function, we already put, that was log base 2 of x. The domain, negative infinity, because it's going to point left now forever, up until 0, not including 0. And the range is negative infinity to infinity. So hope that was helpful.